Welcome to section 6.4. We're dealing with an application of vectors and what we call dot products. The majority of this section is actually a physics section, and so you'll see kind of the application of physics, but we want to get you some of the basics first. Before we start, we want to talk about these two vectors v and w, and so let's look at them. These two vectors v and w are in component form, which means they start at the origin and you can see the movement. And we want to talk about what we did yesterday. In 6.3 we did the addition. And if you do the addition, we said, okay, add the x's, so 2 plus 6, and add the y's, 4 plus 9, and you end up getting a new vector then, 8, 13. Okay? Is this answer a vector or a scalar? Because it's in still component form, this is a vector. All right, we also did scalar multiplication where we took the numbers, like a number 7, and multiplied by the vector. And we said, okay, take 7 times the x value, and then take 7 times the y value. And if I do that, I get 1428, still in component form, which means my answer is again a vector. And so yesterday, those are the things we looked at. Today we're going to talk about a dot product. And you don't necessarily multiply vectors, you multiply lengths. And so we've put this in a box for you because we're giving you vector v, v1 and v2 are its components, and vector w, w1 and w2. And the multiplication of it, which we call a dot product, takes the x values and multiplies it, takes the y values and multiplies it, and adds those two together. Okay, so take a look. Let's do the v and the w that we have above. You take the x value of v times the x value of w, and add it to the y value of v times the y value of w. So 12 plus 36, you end up getting an answer of 48. Now if you look, 48 is just a number, so we end with a scalar. Okay, and so we're going to be working on the dot product today, and a dot product, again, you don't multiply vectors, you multiply their components. And so here we go. There are a couple of properties that are on page 460 in your book, and I'm just going to kind of give you the highlights. You can take the dot product of u and v, and still get the same answer as if you take the dot product of v then w. And what that means then, our dot products are commutative. Okay, that means the order that you multiply doesn't change the outcome. If you look at the second property on page 460, it says 0 times vector v equals 0. And basically what it says is if you took 0 times a vector, then you're going to take 0 times each of the components, and then there will be no length to the vector. And so you're looking at this and basically saying you're not going to have a vector because there is no length once you multiply by 0. The third one, if I'm adding two vectors together, v and w, and I then take the dot product with a vector u, what I can do is distribute the dot product to get u with a dot of v plus u with the dot product of w. So what is this property? This is just using the distributive property with vectors. Okay. The fourth one is actually what I think is the most important and the one we're going to use the most often. It's the idea that if you take the dot product of a vector with itself, what you end up finding is it's the same thing. Let me make sure I have the right letter. It is the same thing as the magnitude squared. And it's like doing Pythagorean theorem, and we're going to show you that kind of as we go through. But basically you want to know that the dot product of a vector in itself is the same thing as the magnitude squared. And I'm actually going to circle that whole thing because, again, that's in the end going to be one of the most important things we've used today. The last one is if I take a scalar times the dot product. When you do a scalar, you either take the scalar to the first one and then do the dot product, or you take the scalar of the second one and then do the dot product. And so as you look, scalar only attaches to one vector only. Okay, there is no distribution because you don't have a plus or minus in your parentheses. So there is no distribution. So what we're saying is you can pick which vector you want it to attach to and then do the dot product. I think you'll find you normally do the first vector just because it's habit, but that's the idea. Okay, now we're going to show you how to find the angle between two vectors, and I'm going to show you how the formula came about, and then we're going to use it. Actually, I'm sorry, I modified my notes since then. What I want you to do is look at example 2 on page 461, which actually does show you how that works. And then I'll go through it together in class tomorrow. But the way it works, the angle between two vectors, if I'm trying to find the angle, I take the cosine of the angle, and I do the dot product of u and v, divided by the magnitude of u times the magnitude of v. Okay, now here's one thing. I'm going to give this to you on the quiz. Okay, so it's going to actually be at the top of the page on the quiz so that you have it, so it's not something that you have to memorize. But again, I want you to take a look at these so that you're aware of what's going on. Again, take a look at page 462. What I would do is grab a separate sheet of paper and actually take notes on these two. And we're going to kind of talk about them again in class, but I want you to make sure you've really looked at those. So let's take a look at the formula. Okay, we're going to find the angle between a vector w, or 5, 8, and 6, 1. Okay, so here's what I'm going to do. I'm going to start by drawing those. 5, 8 means you start at 0, and I go to the right 5, and up 8. Okay, my initial side goes to my terminal side. I'm going to label this w. And then I've got the vector 6, 1. And let me change the color so we can see the two vectors. If I start here, over 6, up 1, okay, that's vector v. And what we're trying to do now is find this angle here, theta, between the two vectors. Okay, so we have a formula, and I'm going to start with that formula. The cosine of my angle is the dot product of w and v divided by the magnitude of w times the magnitude of v. Alright, well, I need to look at a little bit of stuff first. So here I'm going to do a side note. The magnitude of w means take Pythagorean theorem, and we want to find the hypotenuse, basically, of the triangle it makes with the x-axis. So 5 squared plus 8 squared, and we square root that. 25 and 64 makes the square root of 89. And I'm going to leave it in terms of that for right now. I also am going to need the magnitude of v, so the square root of 6 squared plus 1 squared, so 36 and 1 is 37, so I have the square root of 37. And I'm going to leave those for a side note for just a moment while you do my formula now. Okay, as I look on top, the dot product means multiply the x's, so 5 times 6 plus multiply the y's. 8 times 1 all over, if I look at my magnitudes, I have the square root of 89 times the square root of 37. Okay, so I'm going to do a little math here a second. In the numerator, we have 38. In the denominator, when I multiply the square roots, I get the square root of 3,293. And again, my goal is to find the angle. So if I say that the cosine of my angle is this, in order to find the angle, we're going to inverse cosine. So my angle is the inverse cosine of 38 divided by the square root of 3,293. And I can stick that directly in my calculator. And let's round to the nearest tenth. This is about 48.5 degrees. Now again, make sure you're in degree mode so you're actually getting an answer you understand rather than radians. But we're looking at this going, okay, is it about a 45, just above a 45 degree angle? I would say yes. And so we're going to give you this formula. Biggest thing though is you have to know how to use it. And we've gone through one. We will go through more once we get in class. Okay, let's flip the page. I'm going to change my color to a better color too. All right, there is a different form of the dot product. And so I just want to show you kind of how that comes about. It goes like this. If you know that the cosine of an angle is the dot product divided by the product of the magnitudes, okay, then what I want to do is look at it in terms of the dot product. If I want to find just then the dot product of u and v, but I know the angle, what I want to do then is I could take the magnitudes of u times the magnitude of v, which is this denominator, and I'm just going to move it to the other side, multiplied by the cosine of my angle. And this again is another form of finding the dot product. You will use this less often, but I want you to see it to know where it comes from. Basically, again, if you know the first formula, you can modify it if you need the dot product. So the next example says, what if the dot product between the vectors, what is the dot product if the angle between the vectors is 90 degrees? Well, let's take a look. I don't know what u and v are, so I don't know their magnitudes, but I do know that the cosine of the angle is 90 degrees, and the cosine of 90 is just 0. So what do you get? Well, then the dot product of u and v is just going to be 0. This is an actual definition, and this is called orthogonal. Orthogonal is just another word for saying perpendicular. Okay, so these two vectors are perpendicular if and only if their dot product is 0. And let's talk about that for a second, because if the angle between the two vectors is 90 degrees, as I look at a picture, if I have my two vectors u and v, and this is a 90 degree angle, then of course vector u and v have to be perpendicular. And so we should be able to see is if I try to do their dot products, and I don't know anything about the angle, but if I try to do their dot products and I end up getting a value of 0, then I know that these two vectors have to be perpendicular, or what we call orthogonal. Okay, we want to look at this idea of projections. So let me slide this down. I'm going to go through what the idea is. This is a very physics application. So those of you in physics may have already seen this. My pen seems to be acting up at the moment. I'll try writing that somewhere else. All right, this is a physics application. Okay, so I'm going to draw this picture. You want to find the projection of one vector onto another. And a projection, really, all it is a shadow, okay? And so that's one thing to keep in mind, that a projection, all we're really talking about with this idea of a projection is the shadow. And so I'm going to draw a picture kind of as we look at this. Okay, I have this vector u, and let's say I have this little vector v. Okay, and we know shadows. Let's put my sun like right up here. So we have this sun on u, and it's going to project down on u, and u is going to create a shadow. Now, let me change this a moment because I want you to see what happens. When I make this shadow creates a 90 degree angle, and so this red vector down here is the shadow. Okay, now we're going to call this shadow, this whole thing here, we're going to call this W1, and W1 is always what we call our shadow. So I'm going to stick that over here. W1 is what we're looking for. It's the length of the shadow. Okay, now as I look at W1, W1 is on V, it's in the same direction, and so I can think of W1 as a scalar multiple of my vector V. Because it's in the same direction, it's on that same thing, it's just a little bit bigger. So if I look at this picture, it's kind of like we multiplied the vector v times 1.5-ish, and I don't really know the exact answer, but that's what it looks like. Okay, we also have this length here, which we're going to call W2. And W2, that perpendicular length, is really just going to help us find the length of the shadow. Now, if you take a look at this, you'll see that U is bigger than V. And because U is bigger than V, the shadow will also be bigger than V as we go through. So kind of keep that in mind. Okay, so in order to find the projection, here's what we're going to do. The value of U, okay, we're going to start off with an assumption that U is the shadow plus this other length, W2. Okay, and so our goal is to make two vectors, and this will always be the case. You'll have two vectors where basically the hypotenuse ends up being the shadow plus the orthogonal vector. Okay, and so I'm going to rewrite W1 as a multiple, a scalar multiple of V, like we did over here, plus W2. Okay, now I'm going to do something slightly different, and this is one of the things you can do with projections. I'm going to take the dot product with vector V on both sides. So it's like multiplying both sides by a reciprocal or something like that. I'm going to do the dot product. And so what I'm going to do is I'm going to basically take the dot product of U and V here, and I'm going to take this whole quantity and do the dot product of V. So scalar times V plus this length W2, and let's see what happens. Well, if I multiply C times vector V with the dot product of V, I get C dot product of V plus the dot product of W2 with V. Okay, so let's start modifying this slightly, shall we? As I look at this, we know by the property in the front that if I take the dot product of a vector with itself, it's the same thing as the magnitude of that vector squared. And I also want to talk about these two. If you look at your picture, W2 is this perpendicular side to V. And now even though they don't touch, they're still going in perpendicular directions. So this is going to end up being 0 because W2 and V are orthogonal. Okay, so if I look at my picture, even though they may not touch, they're still perpendicular vectors, and therefore their dot product will equal 0. So I have the dot product of U and V equaling a scalar C times the magnitude squared. So I'm going to divide by the magnitude squared in hopes of getting this scalar by itself. Okay, and then let's see if I can look at this. This value of C is the dot product divided by the magnitude of V squared. And what I'm going to do is I'm going to take this, and let me change color so you can actually see it. I'm going to take this and I'm going to plug it in so I can find the projection, which we call W1. So W1, this shadow or this projection, is found by replacing the scalar with the dot product of U and V over the magnitude of V squared times vector V. And this, if you look at this, the question is, what does this mean? Okay, this is all a scalar because the dot product ends up getting you a scalar and the magnitude squared ends up getting a scalar. So this is basically going to be a scalar times a vector, which is going to equal a vector. And we want the vector for the W1 or our shadow. And our goal is to find basically what is component form of that vector. So here's what ends up, through all of that, here's the formula we end up getting. And the way we write it is we say the projection of U onto V, so the V is the little one, is found by doing the dot product of U and V over the magnitude of V squared multiplied by vector V. And this is the same thing in all of our pictures as W1, and we're going to kind of use W1 the whole way through. Now, here's another great thing. I'm going to give this to you on the quiz. Okay, so you've got some time to work with this, but we want you to show you how it works. And again, our goal is to look for this shadow length and basically be able to figure out what is component form of the shadow. Okay, now we're going to use this formula for our last example. Let me see if I can find a better color. Okay, so find the projection of U onto V and write the sum of U as the two orthogonal vectors. So what they're saying here is write it with W1 plus W2 like we did above. It's the sum of two orthogonal vectors. Okay, so I don't like this 3i plus 2j. I'm going to write it in component form of 3, 2. Same thing, this is in component form, this is I and j form, but as I look at this, let's start by writing U. 1, 2, 3, up 2. So here's my U. Let's look at V, 5, negative 1. So I've got to go negative, I better write that in. 1, 2, 3, 4, 5, negative 1. Here's V. Now take a look. Is U smaller than V? The answer is yes. Because U is smaller than V, then our shadow or our projection or our W1 is also going to be smaller than V. So as I look at this, this is going to make a 90-degree triangle where this length right here is my projection. Okay? So you're always going to want to draw a picture and you want your U to make a right triangle with vector V. Sometimes W1 will have to be bigger if U is bigger than V, and sometimes your W1 will be smaller if U is smaller than V. Okay? So let's start writing our projection. The projection of U onto V is found by doing the dot product divided by the magnitude of V squared multiplied by vector V. Okay, so we got a little work to do. Let me do some side work a second. Let's find the magnitude squared. Okay, so normally magnitude, we'd say 5 squared plus negative 1 squared. But if we're squaring it, this whole thing gets squared, and the squared and the square root go away. So 5 squared is 25, plus 1 gets you 26. So the magnitude squared is 26. Let's look at the dot product of U and V, because I also need that. 3 times 5 plus 2 times negative 1, 15 and negative 2 is 13. So if I look at this, let's do it this way. 13 over 26 times vector V, which is 5, negative 1. Well, 13 over 26 is really 1/2 if we wanted to write this. But if I do 5 times 1/2, I get 5 halves. Negative 1 times 1/2 is negative 1/2. So this is my projection of U onto V. This is the component form of my shadow. Okay? And if you wanted it in decimal, you could say 2.5 and negative 0.5. That's fine. And you can kind of see it's about 2.5 down a half. Based on how accurate your drawing is, but this is an approximation. My drawing is approximation, this is an exact. Okay, now our goal, though, that's the first part. The first part they say, find the projection. Number 1, we've just done. Number 2, though, says, write this U as the sum of the two orthogonal vectors. And so as I look at this, I'm going to go, let's change our color so we can kind of keep these straight. We'll make number 2 red. As I look at this, I want to say that U is W1 plus W2. Well, I know vector U is 3, 2. And I know my projection is 5 halves, negative 1/2. But I don't know W2. But I can find W2 if I subtract this vector, negative 1/2, or add the opposite, right, is what we did in section 3. So if I add the opposite of vector W1, then I get that W2 is 1/2, 5 halves. okay? So if I'm going to write this sum, they actually want to see it out. Where you say, okay, in order to get the vector 3, 2, I add my projection, 5/2, -1/2, plus my W2, my orthogonal vector of 1/2, 5/2. This is part 2. Okay, and it's really saying, do you understand that you can kind of solve equation with vectors like you do normal equations? Okay, so that's section 6.4. We'll be working again with more projections in class, but the idea again is that the projection idea is really you're just trying to find component form of a shadow.